Hello everyone. In today's lesson, we are going to look at how to represent complex numbers graphically on an Argand diagram, or what we call the complexing plane. Now, we should first understand that complex numbers can be represented graphically just as coordinates are. But x-axis is going to be substituted with the real axis, okay? And in the same way, y-axis is going to be substituted with the imaginary axis. Let us consider the first complex number z, which is equal to 3 plus 4i. This means that for z, we are going to move 3 units along the row axis, but from the origin. Okay, so we move 1, 2, 3 steps. Okay, thereafter we move 4 units parallel to the imaginary axis, but perpendicular to the real axis. So we move 1, 2, 3, 4 up to there. Okay, it is clear that the complex number z specifies the direction from the origin. Therefore, we are supposed to use an arrow to connect the origin to the last point, like that. Okay, we observe that there is an angle created from the real axis up to that point, and this arrow has length or size. Therefore, we are tasked to find this angle called theta and the size of the complex number z. The question is, how are we going to obtain them? It is very, very simple. Okay, we first draw our right angled triangle like that, and after drawing it, we see that we can have the opposite of this angle, which is equal to the imaginary part, and then the adjacent of this triangle, which is the real part. Okay, so to obtain an angle theta, we shall say theta is equal to tan inverse of the opposite out of the adjacent. Okay, so theta is equal to tan inverse. The opposite is the imaginary part of the complex number z, and the adjacent is the real part of the complex number z. Therefore, theta is equal to tan inverse. The imaginary part is 4 and the real part is 3. So theta is equal to, let's get our calcs and obtain the value of theta. So theta is equal to 53.1 degrees in an anti-clockwise direction. Okay, so let's obtain the length of z. So we shall say the length of z is equal to the square root of the real part squared plus the imaginary part squared. Okay, so the size of z is equal to the root. Real part is 3, we square, then the imaginary part is 4, we square it. So this is equal to 3 squared, that is 9, and 4 squared, that is 16, and the root, implying that this is the square root of 25. So the size or the length of z is equal to 5 units. Okay, example number 2. In example number 2, we have W as 4 minus 2i. Okay, what does that mean? We are going to move 4 units from the origin along the real axis. So we start, this is 1, 2, 3, 4. Thereafter, we move 2 units downwards. Reason being, the imaginary part has a negative symbol. So we move 1, 2. Okay, so we draw an arrow from the origin up to that point. We create the right angled triangle. So it is clear that from the origin up to this point we have 4 units, and then from here up to here we have 2 units. We have an angle theta, and we need to obtain the size of W. Okay, so to obtain the value of theta, we shall say tan theta is equal to the imaginary part of W out of the real part of W. So theta is equal to tan inverse. What is the imaginary part of W? That is -2, and the real part of W, that is 4. So theta is equal to tan inverse -2 out of a 4. Let's obtain the value of theta. So theta is equal to -26.6 degrees, or theta is equal to 26.6 degrees in a clockwise direction. Okay, we are moving from the positive real axis, moving downwards in a clockwise sense. Let's obtain the size of W. But we say that the size of W is equal to the square root of the real part of W squared plus the imaginary part of W when it is what? Squared. So the size of W is equal to, the real part is 4, we square it, and the imaginary part is -2, we square that one. So 4 squared, that is 16, and -2 squared, that is a 4, and a root. So the size of W is equal to the square root of 20. We place our calculators and we get the value of the square root of 20, which is equal to 4.4721 units. Thank you for watching. Don't forget to subscribe, like, and share the video for more about